Do inductors have polarity? As I've written in my summary sort of document, basically in general terms, inductors do not have actual polarity like positive and negative. However, they do have beginning, and specifically more so, only obviously in a multi-layer inductor or inductors type of thing, not in a single layer inductor. Over here you can actually see beginning, you can see the end, and they're on the same level, exposed, wherever. But nonetheless, on a multi-layer, it seems that there is not as such as polarity, sort of plus and minus of the coil, but there is a beginning and there is an end of the actual winding. If you look at it very carefully, you will see over here, let me just zoom properly, you will see on this inductor, this is the start of the winding, then it's wound, and it has got several sort of layers, and then you end up with the very last sort of layer and the last sort of piece of wire which is connected over here. So in actual fact you got the beginning and you got the end, and I'll show you what I mean on the actual paper. It's something like this. You got the basically beginning of the coil, which is wound. Okay, this one has got only 2 layers, and then you end up with the outer layer. Okay, and on some coils, of course, it's marked the actual beginning of the coil. Okay, type of thing. So for easier identification, not all of them do have it, but some of them are marked. Now, it seems that it matters heck of a lot. Okay, and why it matters in a switch mode power supplies for EMC reasons, due to the way inductors are designed and manufactured, as well as the way they are actually energized, specifically in a switch mode power supplies. Okay, so now let me go to another sort of setup. This is my basic setup. Okay, I got a generator, okay, which I'm gonna apply across the actual coil. Okay, so you can see the circuit is closed. Basically, generator is connected to the coil over here. Okay, and it's connected over here. So basically, the signal generator is applied right across the coil, and that's what I'm gonna do. Apply the signal generator, okay, across these 2 points. And the only one thing that I'm gonna do, of course, here is my coil, okay, with exactly identical to this one here, okay, and basically I'm gonna put a square wave. I've chosen just for demo purposes. It happened to be 2,979 megahertz, and it is a square wave for a specific reason, and that is because you can see definite rising and definite falling, and the sharper the sort of transients, the more magnetic field the coil will switch on more abruptly, and it will create a bit more firmer and stronger magnetic fields, stray magnetic fields and so on, which would be easier to measure. And then, of course, coil will be connected. The dot represents the beginning of the actual winding of the actual coil, beginning of the actual coil. Okay, and the only thing that I'm gonna do is eventually, let me just put it down, having a coil like this connected, okay, in circuit. The only one thing that I'm gonna do is I'm gonna take the same coil and I'm gonna swap it. I'm gonna turn it from there to here. In other words, the beginning becomes over there of the inductor, and the end of the inductor is now to this side. And then I've got a spectrum analyzer with a special probe, connected spectrum analyzer, basically connected with a special probe, okay, across the actual, close to the actual windings. And the object of this sort of video is that I'm going to demonstrate just now is to see the difference. Does it make a difference if I swap the coil? I apply still the same voltage level, I still apply the same frequency, and let's see, does it really matter which way it is connected? And according to Maxwell equation, basically it states the rapid change, okay, and that is dV dt, voltage over, let me just show you, okay, the rapid change dV dt is particular point, at particular point is where the highest sort of EMI noise will be actually generated, electromagnetic field, and which is usually a point of the inductor connected, if you look at it over here, connected to the a switching, or should I say noisy node, because this is where all that switching is actually done. So we got to say positive applied over here of the coil, and with this MOSFET, this inductor, well, this is like a buck converter, keeps on switching this side of the coil to the ground. But it happens very fast, and in this particular case, I'm using 2,9 something, 2,973 I see on the spectrum. 2,978 megahertz. Okay, and I will swap the legs of the generator and then see the actual difference. Is there a difference of electromagnetic field that gets picked up with the probe into the spectrum analyzer? All right, so without any sort of further delay, let's start and let's see what happens. Okay, now I'm going to apply, say for argument's sake, apply, okay, wait, let me just put this in properly. Okay, so makes a good connection. And then I connect up a generator, and voila. Okay, right now the spectrum analyzer is showing me a 2,987 megahertz. Okay, let me reset again one more time. Okay, can you see over here? It will take few seconds to sort of scan over a period of time and pick up a highest peak. And right now, 2,98, okay, there it is. It picks up, and now it's going to lock. Okay, so it has actually given me something like minus, I'm just going to write it down here, minus 51 dBm. Okay, and that is one-way connected. My negative connected there, say, of the generator, and a positive signal of the generator connected to the top. The only one thing I'm going to do now is I'm going to swap it. And this is what I'm going to do. Now I'm going to put it at the bottom, okay, the positive of the generator and negative over here. And watch now what happens. Okay. Voila. You can see it's gone down to 64. Okay, let it give it enough time to settle. You will see on the instrument over here. Okay, that's it. It locked on 62.5 dBm. 62.5 dBm. Okay, so basically one way generator connected. Okay, let me just do this. 62.5 minus actual fact, the difference between 62.5 and 51 dBm is approximately 11.5 dBm when the coil is actually reversed. So one way, okay, and 62 means 168 millivolt, microvolt is actually measured by this probe that goes into a spectrum analyzer. And minus 51 dBm means 631 millivolt. And that actually gives us, depends how the coil is connected, okay, whether it's connected this way or it's connected with the beginning of the winding to the other side, gives us a difference in emitted noise of something like 463 microvolts, which is a substantial amount of noise actually generated. And what you call it, and that can be actually a very big factor, what you call it, in how you actually connect the actual inductor in the switch mode power supply. And as a result, properly fitted multi-layer inductor connected to a switch mode power supply, wherever, or over there to a switch mode power supply, properly connected with a basically starting winding connected to the noisy node. Okay, so that's a inner. That's the beginning of the actual coil, which is the inner part of the coil, is actually shielded by the all other layers, and eventually the final sort of winding wire connected to the, I call it a quiet node, or well, it's called in the industry the quiet node, because there is no noise coming from here. It's only a pure sort of square wave that I'm applying. So, in actual fact, the outer layer acts as a shield, and the coil starts emitting much less electromagnetic field and noise, and that's why if I reverse it opposite and I put the, say, beginning of the winding here, then obviously my noise jumped. In other words, I just reversed the actual coil, let me show you on the coil itself. Instead of, say, having it this way, okay, and then having it this way, gave me a difference of 463 microvolt. It's difficult to describe, but it's a ginormous sort of noise generated just by putting this inductor wrong way. So basically, the reason why it actually the outer windings, you get the beginning and you get the sort of next winding, and so. So the outer winding basically creates an electrostatic shield, and of course that electrostatic shield, as I said just now, attenuates radiated electromagnetic field significantly by like 463 microvolt, which is ginormous sort of figure. Although the number doesn't seem that big, but that is extremely powerful sort of signal which can radiate all over. And the difference how you actually put the inductor, okay, can reduce harmful emissions within that powers from that coil in the electronic circuit where you're going to use this coil, where you're going to use, say, this coil that I'll be measuring, okay, can reduce harmful emissions by up to 15 dB. And 15 dB means basically approximately 50 times lower sort of emissions and interference and noise you will be getting generated with this from this coil, which can actually make why is it significant? Because it will make a big difference between bad, failing, or good, passing limits, basically for the EMI, and that's electromagnetic interference, and for the passing and operation of the switch mode power supply. So it is very, very essential. So the long and the short, basically, it does not have polarity, but it matters which way you connect it up. The beginning and the end of the actual coil. So just to summarize everything what I have said, always make sure. Let me just take my document over here. You can see over here, you can see starting wire. This is, you can see over here, it's an outer shield. Over here, it's an outer shield. And over here, it's a starting winding. Okay? Top 10. So, as I stated over here in my sort of summary, always make sure that starting wire of a multi-layer inductor winding is connected to a noisy node, okay, starting of the actual multi-layer inductor. And end of the winding, which is the top layer, okay, which creates that electrostatic shield and protects emission of the, stops the emission of the actual electromagnetic noise and I mean the noise generated from the electromagnetic whatever. So an end of the winding wire connected to quiet node, which is over there. And then you will have no problem, and it will improve the performance of your switch mode power supply, and it will be more in compliance with whether it's a European, American, or Chinese, or wherever standard sort of type of thing. Although it looks like a very simple thing, but interference and noise, because power supplies are becoming smaller and smaller and they're operating at much higher frequencies than what they used to in the olden days, it become extremely essential. Whether it's an inductor like this, or whether it's just a blown up picture, whether it's a 3mm inductor, once it's a multi-layer inductor, then it's a very, very essential which way you're going to actually connect it up in your circuitry, electronic circuitry. Yeah, on that note, I say thank you for watching, my sort of introduction to the an explanation, do inductors have polarity? And now you know why and what's actually happening within. Thank you for watching. Till next time.